and calibrate your accelerometer and force sensors. And also, if you haven't collected the mass, the objects that will increase the mass of your IOLAB, go ahead and do that too. I used like large soup spoons, the same ones I used for the force of friction experiment. It looks like we have 2 more people to log in, so I'll wait just about a couple more seconds. All right, thanks, Brendan. That should work pretty good. You gotta have like Scotch tape, cellophane tape of some kind to attach them with. Excuse me. But and this time, I guess because the IOLAB is going to be hung from the long spring, if you don't have cellophane tape or Scotch tape or masking tape or anything like that, you could probably use like a hairband or something to make sure it attaches on there, rubber bands, because it's not going to roll. It's just going to, oscillate up and down on top of the hanging from the spring. That cellophane tape works. Okay, so I'm going to go ahead and get started because it's now 11 minutes after 10. We're 1 minute past. So I'm going to go ahead and open up my notes and we'll get started. So here we have simple harmonic motion. And of course, we're going to determine the known mass of the IOLAB. Well, we're actually going to do it like 3 different times in order to get the mass for each of the parts. We have part 1, part 2, and part 3. And in part 1, it's the original mass of the IOLAB, which is nothing attached to the IOLAB for increasing its mass. But as you can see here, it'll be hung from a spring. And I've got the spring attached to the binder clip, and I've got a binder clip inside of a book, and the book is like on the edge of a tabletop or a shelf. But in order to determine the known mass of the IOLAB, you did like you did before in the past, where you put the eye screw into the force probe. And this is, of course, after you had done your calibration, so you can get a better value. So make sure you've calibrated your force probe and your accelerometer, magnetometer, and gyroscope thing. So make sure that everything is there. So once you get that done, then you're going to determine the known mass and just basically follow the instructions again, and you'll write in the values, those average values, because you're going to click and drag across the region where you're actually holding the IOLAB up in the air by the eye screw. And then you record the acceleration, which should be really close to being the acceleration of gravity value, and the force. And when you determine the mass, when you take the force divided by the acceleration, you should get something close to 0.2 kilograms. If it's pretty far off from 0.2, like maybe 0.22 or 0.26 or 0.25, that's way too much. Try recalibrating and do it again. Because sometimes I found that my calibrations, I'd have to do it like 2 or 3 times in a row in order to get it to really sink in to the software. So we do that. Now, we've done the known mass, a few times before in other experiments. So I don't need to have screenshots of it, but you can if you want to. That way you'll have screenshots in case something happens. You can go back to it, but also you can go to the folder in the IOLAB and you can look up the old data and check there if you need to go back and take a look at it. But screenshots of all the other parts of this experiment is necessary. So you're going to have 3 screenshots per part. So we have part 1, part 2, and part 3. So you're going to have 9 screenshots. Okay. So we're going to start with the original mass, no added mass, the IOLAB, 2 more sets of data for more total amounts of mass to be used. Okay, got that right. And Brendan says he's got the soup spoons, and anybody else, you can use whatever you like that will increase it a fair amount. I mean, I had one person try to just attach a nickel to the IOLAB, and that was not enough mass to get a good change in the data. A soup spoon is probably around 30 to 50 grams, so that's a good increase. But you also have to be careful not to put way too heavy of a mass on there because you can overstretch the spring and damage the spring. Which also led me to the idea of when we're doing the simple harmonic motion, well, simple harmonic motion means, well, simple means, it goes straight up and down through a single line. It doesn't like go waving back and forth. So you're going to have your IOLAB oscillating up and down vertical as best you can, no side-to-side motion whatsoever. If you can at least, trying to do that. If there is side-to-side motion, stop it and try it again. But try and keep it going as vertical up and down as possible when you allow it to oscillate. Another thing is, in the video on the online manual, the person in the video, which shows you, they're actually pulling the IOLAB down and then releasing it to go start the oscillation. I found that sometimes people don't know how far to pull down, and they may damage the spring, or they may shoot the thing up and that kind of stretch it too far. An easier way to do this and to make sure that you've got it right is instead of pulling down, and this is the equilibrium position right here. So when the IOLAB is hanging from the spring and it's resting, then you'll see the spring is stretched and everything's at the equilibrium position. If you were to lift up a couple of centimeters, but still keeping gaps between the coils of the spring, they're not touching each other, then you just merely drop it and send it oscillating that way. That way you know that you're not overly stretching, because you're not really stretching the spring and maybe causing any damage to it. So lift up, making sure there's still a little bit of gap between all little coils, and then let it go, just drop it, and make sure it's going straight up and down when it goes to the oscillation. So we'll do that. Let's see here. So when you do that, you're going to collect data with the IOLAB. And when you do collect, okay, listen to this. When you do collect, because it'll make taking the data for the fast Fourier transform much easier. When you do collect, make sure that the accelerometer is still on, is still checked when you are determining the mass of the IOLAB. So we have the accelerometer and we have the force probe. So you take data and you're going to get something similar to what I have down here. This is just showing the force probe. And so you get these oscillations, okay? And in the first part, they're asking you to take oscillations for 60 seconds, okay? Now, even though, I'm not sure if you can tell here, probably you can tell, the amplitude of my oscillations as time goes on seems to be a little bit smaller, a little bit smaller, a little bit smaller. Okay, and that's okay. There's a little bit of friction of the spring in itself when it's moving up and down. Plus there's this air drag, which is going, or air resistance going on. And so it's going to slow down. Well, it's going to, the amplitude is going to get diminished. However, and this is one of the great things about pendulums and with oscillatory motion, springs up and down, is that the amount of time that it takes to go through one whole oscillation, and the time it takes to go through one whole oscillation is called the period, does not change, even though the amplitude is changing. So the period is independent of the amplitude. You can have a large amplitude or you can have a small amplitude, but the period of oscillation will stay the same for a particular spring constant and for a particular mass that's on the spring. If you change the mass, then you're going to change the period, of course. But it doesn't matter how big the amplitude is for a particular mass and for a particular spring constant, it'll have that period. And they're wanting you to show that in this first part one, where they're going to take the time for 5 oscillations in the beginning of the data set, and way at the other end where you have like 50 to 60 seconds, they want you to take again the amount of time for 5 full oscillations, and you'll see that the two numbers are virtually the same value. I mean, the only reason why they're off a little bit is probably due to where you put the cursor on the screen and take your data. Okay, so back up to here. So through the derivation that you see on online manual, they finally get to the point where you have that the angular frequency, okay, that's the omega, is equal to the square root of the spring constant divided by the mass of the object hanging on the spring. Okay, so we have the mass of the IOLAB, plus whatever mass is for the part 2 and part 3, the increased mass. The spring constant stays the same because we're using the long spring. And then once you've got that, then that's how you get the angular frequency. So what we're going to do is we're going to find the angular frequency that we're going to get. And since we're changing the mass, we're going to be able to get data and plot it on a graph. So if you take a look at this equation and set it up this way, so it looks like a power curve, okay, y equals ax to the b power. So omega is the y, and the constant, the coefficient right there, a, has to be the spring constant, so that's the square root of k, so that's your a value. And since we're changing m into some power, that's going to be the x to the b power. So the x is our mass, and the y is our omega. Okay. And from this, we should be able to get a coefficient, which is going to be the square root of the spring constant. And as you can see on the worksheet I put on there, the people who put this experiment together, they say that the long spring has a spring constant of 11.5. So you'll take 11.5 and take the square root of that on your worksheet, and that'll be the number we're looking for. We're going to compare the spring constant. Okay. Now we have omega this way, but how do you determine omega for the experiment? Here we go. Okay, determine the angular frequency from a plot of the force versus time, which I've got just showed you down here. Okay, we'll do that. So what you're going to do is, I've got two screenshots here to show what I'm trying to show here. So once you've taken the data, then you can click on the analysis mode, and you can move the cursor around, and you can stop the cursor on the very first peak of the waveform here, of the oscillation. And you'll get a time. I've got a time here, it says 0.3917 seconds. That's going to be your zero time, let's say, your beginning time. And this is your zero peak, okay? They want you to measure 5 full oscillations worth. So as you can see here, you start off at the zero peak, then you go 1, 2, 3, 4, 5, okay? That's what I got here. I got 0, 1, 2, 3, 4, 5. I'm counting like that because some people will make a mistake and do a miscount. They'll see the first peak as the number 1, and they'll go 1, 2, 3, 4, 5, but that's only 4 complete oscillations between 1 and 5. From 0 to 5, which is what I've got here, is 5 full oscillations, because you go from peak all the way through to the next peak, that's 1 oscillation, to the next peak, that's 2 oscillations. And so you get to the fifth oscillation, go through 5 oscillations, and you get to that peak right there, and you get the time there. Subtract those 2 times, and that's a time for 5 oscillations, which you put on your worksheet, okay? Then just divide that number by 5, and that'll give you the time for 1 oscillation, and that is the period of oscillation. To get to omega, the angular frequency, all you really do is take 2 pi and divide it by that period of oscillation, and you've got the angular frequency. Okay, so that's how do you determine the angular frequency using the period of oscillation for part 1. But they're also asking, we determine omega a second way. And this is by using the FFT. We have the ability to use the software in there, and they have the fast Fourier transform of the data. So you'll select so many bins worth of data, and it will work on the determination of the frequency. And you'll get like a couple of different frequencies, and kind of like a little Gaussian distribution of some frequencies are kind of there, and other frequencies are kind of there. There's one that's like majorly there. Even though you think that's going to be one frequency here, there are subtle little changes, because the way my data is taken, because you can see right there, that one right there doesn't look as good as the others on either side. So there's a little bit of a glitch right there as it goes through, and there's another one there. So on the most part, I'm going to get a peak frequency that the fast Fourier transform is going to give me. But it's going to give me other frequencies which are not as representative, and I'm going to choose the peak frequency. To give you an idea, I'm going to stop sharing this, and I'm going to go to the ILAB software I had taken earlier. Okay, everyone can see that, and you see here that I've got nice oscillation in the force. And you see I've got a little bit of a glitch right there. I've got a little bit of a glitch right there and taking the data. So it's not perfect, but it's pretty close. So down here, we're using the force probe. Down here, we have the toolbar, and you can click on that, and you can go over here to the fast Fourier transform drop-down menu, and click on that, and go all the way down to 4096. We're going to choose that. Okay. And when I go up here, I'll just left click once. I'm not going to drag. I'm just going to left click so it can lock in that gray region. It's the gray region which is actually using the fast Fourier transform. And you see, as I move around, down below, you can see all the different frequencies it's trying to fit to, but there's one which is really significant. That's the peak frequency. So I'll go ahead and choose this. I'll go ahead and left click there. I can move it down here, and then I can move the cursor down here with that black line and center that black line in the middle of that peak frequency. And I see you have a frequency there. It says V, whatever the V stands for, but it's 1.367 hertz, and that's the frequency F. So we're in the frequency domain. We're doing the fast Fourier transform. So this is another way of trying to determine the angular frequency. We're not there yet. We have a frequency F. All right, I'm going to stop sharing that. We can go back to that later if you need to. Let's see, go back to my notes. Okay. So in this case, we're using the fast Fourier transform. I get a frequency F. That's what I just found, that 1.367. Now I have to multiply by 2 pi. Don't get confused by here with the period, because the frequency and the period are related, but one's the inverse of the other. So we take the frequency and multiply by 2 pi to get the angular frequency. And that's going to also be placed in your Excel worksheet. And you'll see that. Okay. And let's see. So I said here for part 1, we have original mass, and determine the mass of your IOLAB using, as you've done before. Then you're going to hang the IOLAB from the long spring, and while the IOLAB is oscillating, take data. Make sure you have both the accelerometer and the force probe sensors checked when doing that. Determine the period of oscillation, showed you how to do that, and record this in the Excel worksheet and calculate the angular frequency using the period for one oscillation. That's the capital T. Then apply the FFT to the data and get the frequency F, and then calculate the angular frequency in this manner. Now, ideally, the two angular frequencies should be the same number. If they're wildly different, then you need to recheck your data that you had taken, or maybe how you put the calculations in the Excel worksheet. Maybe something was wrong there, but they should be basically the same number. Maybe off by about 0.2 or so, but we'll see. We'll go work on that. So, see, only about 24% different after the second attempt to get data. That's Brendan. We'll have a look at that, Brendan. Okay. So that's part 1. Then you're just going to increase the mass of your IOLAB by attaching whatever you have. Then you're going to go through the same process of determining the mass of the IOLAB by, going to lifting up on the force probe with your hand, just like you do with the known mass. And then you're going to get a mass value, and hopefully you're going to get a number which is slightly bigger in mass than you had from part 1. If not, then recheck your calculations and your data. And then go ahead and attach the IOLAB with the added mass to the spring and go through the whole process again. And continue that again in part 3. Okay, and then we'll do some analysis with a graph. But I'm going to ask everyone to do part 1 and part 2 and part 3 first. And in part 1, if you're having some discrepancies, like Brendan just said, he had 24% difference, which is kind of high, then we'll have a look at it. But if you've got a low percentage, like that's less than 10% between the two omegas, then go ahead and go to part 2 and do this whole thing again. Do part 3, do the whole thing again. And when you're done with all 3 parts, type in the chat, done with part 3. And then I'll know, then we'll go ahead and start talking about the graph. Does everyone go with that? Hopefully. Maybe you're all working right now. Okay, so I'm going to stop sharing this. And I'm going to go to make everyone a presenter so I can see if anybody has any questions like Brandon may. Right, when doing the known mass or considering, you can if you want, but I'm not all that concerned about getting the known mass for all 3 parts. It's the other ones where you have, it's written on your worksheet. The K value is written on the worksheet. It's also in the online manual. can make everyone a presenter. You're welcome. And Brendan, if you could share your Excel spreadsheet, let's have a look at that. Let's see what's going on there. And if you could increase your percentage from 100% so I can see it better, it's like really small on my screen. You could zoom in, go to the lower right-hand corner of your Excel and just increase the percentage. Or you do it that way. There we go. That's better. Thank you. That's good enough. So you got an angular frequency of 6.4 doing the period, and then you got an angular frequency of 8.5 using the FFT because you have the same 1.367 that I got. Okay, so I believe the FFT one, the period of oscillation, let's look at that. So if you could go close this Excel down and then open up the iLab software for the oscillation, let's take a look at that. Okay. So, yes, you can zoom in and then you can take a point there. And then, here, try this. Yeah, you're going to do that. So it's 1 right there. So 1, 2, 3, 4, 5. Perfect. Now, if you look at the, it should give you a delta T. See that 3.91252? You can also do it that way. It already does it for you. So what time did you have on the Excel spreadsheet? Was it 3.912? Go ahead and pull the Excel spreadsheet back up. And you did have that. Okay, so that's kind of peculiar. I'm going to go to mine. Let's see here. Oh, can you click on the cell for period of oscillation T, where we had the 0.9781, click on that. And you divide it by 4. You should divide by 5, because you have 5 oscillations. There we go. So that's better. Okay, so that's not too bad. So now you're down to a 6.5. Yeah, much better. There we go. It was 5 oscillations, not 4 oscillations. Okay. So go ahead and continue with the rest of it. Oh, it did? Well, maybe they were doing 4 instead of 5. Oh, I bet you they were using the wording from like peak 1 to peak 5, and that's only 4 oscillations. So as long as you're dividing by the proper number of oscillations by the proper number, yeah, that should be fine. So they're probably meant because people, that same mistake that I've had people in the past also do, I go from 1 to 5, that's actually 4 oscillations. Because we're counting the first one as a 1 instead of a 0. Okay, so did everyone see that? Yeah, it does make sense. Okay, Tyler, where do we need to place the data analysis bar on the force graph to do the FFT? I'm going to show you, well, actually anywhere. Let me see. I'm going to pull up my iLab and I'll show you. Okay, so you've got this, and you can move this. You're talking about the gray region, Tyler, that I'm moving around? So I can't see what you said. Let me see. You said yes. Okay, let me go back to that. So actually, you can just move it around, and since I can see that my peak frequency is not moving at all. The other little frequencies it's trying to match up are, trying to match up, but they're not any significant value at all. So you can just put it almost anywhere you want, then left click, and then we'll set that, and then you just go right here and then measure that value right there, the peak frequency. We don't care about these other ones down here because they're not significant. It's that one which is what we're looking for. Does that make sense, Tyler? So this gray region can be almost anywhere on here. As you can see, I can move it all the way down to here, and that peak frequency is still the same. And I'm going to put my notes back up. Especially the part with the two angular frequency equations. Let me see. So we don't need to record for a full minute on the second through. That's correct, Brendan. Thank you for reminding me about that. Yeah, for part 2 and part 3, all you needed like 20 seconds worth or 15 seconds worth. They only asked for the 60 seconds worth for part 1 because they wanted to prove a point about the period being independent of the amplitude. And that's the only thing. So you use the time for 5 oscillations at the beginning of the set of oscillations, and the time for 5 oscillations at the end of that 60-second, and then do a comparison. How do we know which angular frequency formula to use? Ben, well, it depends on which one you're looking at. So if you're finding the period of oscillation, like with when you're trying the time at the first peak and you find the time of the 5th peak, or the 6th peak, 1, 2, 3, 4, 5, then the period t is found from taking the difference of those, the time for 5 oscillations divided by 5, or 4 oscillations divided by 4, like they say in the online manual. And then you get that, and you divide that by that, and you get the period t. So that's this equation up here. When you're using the fast Fourier transform, you're actually finding the frequency f. And that means you have to multiply by 2 pi. And you say, Brendan, so I'm doing click and drag for the time. I could get all the data in one screenshot. If I'm also hovering over the f of t, right, since delta t and the f, and are they all visible? If they are all visible, then go ahead and do that. Brendan, yeah, that one screenshot with the data. As long as you are stating in the caption for your screenshot what's all in there, it should be good. And back to Ben. So Ben, is this okay? So you use this equation up here when determining the period t, and you use this equation down here when you're getting the frequency f from the fast Fourier transform. You're welcome. And while you guys are doing the work, I've been kind of looking ahead at, I think it's the last experiment. Let me see. For some reason, my formula is not working, though. Okay, can you show me? I'll stop sharing that. And if you can share your Excel worksheet, take a look at it, Ben. Okay. Let's go ahead and click on where it says name question mark, and we'll see what's going on there. So you've got, oh, okay. Where it says pi, okay, make sure there's a capital P and a capital I. I think that's what it's supposed to be. And then directly after that, put a beginning parenthesis and an end parenthesis. Right, now hit enter. There we go. So when using the function pi, it's looking for an argument. I guess it's a programming thing. And since there's no argument for the pi, it just asks for a blank inside the parentheses. Now I was looking ahead at, I think it's the last experiment, or is it the second to last? Let me see here. Maybe it's next week, okay? But we're going to have oscillations. We're going to continue with oscillations. We're going to have a string, and we're going to determine, let's see, modes of oscillation. But anyways, we're having a string, we're using a force probe, but there's also a small motor that comes in your kit. And so like a little blue cylinder with 2 wires sticking out of it. And if you were to look at the online videos for that experiment with the vibrating string or oscillating string, it asks you to take some glue and add glue to the part where the 2 wires go in, because the wires have a tendency to break while it's vibrating. And it may not be true for all the motors, or little blue motors, but some of them do. Okay. So there's a video on there which has you wrapping a piece of cellophane tape to make a little well, and then taking some, you can use Elmer's glue or epoxy or whatever, and just put a little bit in there and letting it dry. So I'll send out an email to all the different classes that are going to be using this this motor. And you have to have it glued before you do the experiment by at least a whole day for allow the glue to dry. And now some of the motors already have glue on them from the previous semester. So those are good to go. So have a look in your kit and see if you have a little blue cylinder motor with 2 wires sticking out of it. Either has glue on the end where the 2 wires are coming out or not. Let's see, Tyler. Oh, Matthew. Let me see here. I'm going to pull this back up. Okay. See, the second from omega is right there with 2 pi f. And how do we find FFT? Okay, I can show you that. Then Tyler forgot. What is the method we use to find force and acceleration to determine mass? I know how to calculate it, but don't know how I should proceed to get the measurements. Okay, so what you do is you have the eye screw in the force probe, Tyler, and then you set the IOLab up so the eye screw is pointing up, and the positive y-axis is pointing down on the front face. Then you have the accelerometer on, and you have the force probe on. And this is after you've calibrated both the accelerometer and the force probe. So make sure you do the calibrations first. Then you're going to take data with the accelerometer and the force probe, and you're going to pick the IOLab up by the eye screw, and then hold it there for like a second or two. Make sure it's nice and stable, and then set it back down and stop taking data. Then you're going to highlight the region where you were actually holding the IOLab up in the air, and it'll give you the acceleration, which should be close to the acceleration of gravity. It'll give you a negative value. And it should give you a force during that time, and that's your force. Then you use the force and acceleration to determine mass. Okay, you're welcome. And back to Matthew. How do we find FFT? Okay, I'm going to stop sharing this and go back to, let's see, the IOLab. can't get that. There we go. Let's see, who's... Okay, Matthew, was it the thing under force that shows V? Yes. It's the one that shows V. So you're already there. All right. So yeah, you go here, click on that, which you've already done, FFT, click on that, choose on 4096, and then you're moving this around, click on that, and then move this cursor around, and you can see right there it says V is 1.367. So it's the V one. The one that has, it kind of clues you in with the units called hertz, because our frequencies in hertz for HZ. And the A, I think, is the amplitude, how tall it is. Because you can see how it's above the 0.5. That gives you the amplitude, how tall it is. But we don't want we don't care about the height, except we're choosing the largest height. And we want the frequency, which is that they have for V, at 1.367 for this one. Does that make sense, Matthew? Yeah, okay, great. And then Brandon, you said we need 3 screenshots per section. I think I'm forgetting 1 for section 2. Well, actually, I think it was, who was it? Now I'm forgetting who said it, but they were able to do only 1 screenshot where they could go to analysis mode, go to the first one, go 1, 2, 3, 4, and 5. I can get that on there. There's that. And they shifted this down, and that showed a delta T right there, and that's what that is. Instead of doing like this time minus that time, you get a delta T. It makes it a whole lot easier. Then they also did the FFT, and they put the cursor there, and then took a screenshot. That gives you all the information in 1 screenshot, Brandon. And everyone else, if you want to do it this way too, that's good with me. I wasn't thinking about getting everything on 1 screenshot. And so you got the force, which is giving the delta T for the period. And you've also got the FFT going, and you've got all the numbers on there. And you just take a screenshot of this one, and that's 1 screenshot for all of it. Okay, so I was doing the same, but 1 for the first, yeah. Which gives you 2. So that's okay. As long as I get information for all parts, then it will work. So as long as you are describing in the caption what values you're getting, then you should be fine with either 1 screenshot or 2 screenshots or 3 screenshots, just depending on the data you are trying to retrieve from the experiment. Okay, so Brendan's done with part 3. That's the first person I've seen that's done with part 3. Is anyone else done with part 3? Okay, thanks, Brandon. So as everyone is taking data, you should see that the angular frequency, as you increase the mass from part 1 to part 2 and part 2 to part 3, you'll see that the angular frequency gets smaller. And that goes with the equation we're using in order to graph the data by. You know, the omega goes as the inverse of the mass. So as mass increases, it's on the bottom of the equation. Then the omega, which is your y value, should decrease. So make sure you're seeing that. So part 1 is going to have a certain angular frequency, and part 2 should have a slightly smaller angular frequency, and part 3 should have an even smaller angular frequency. Now to go to Matthew, which value do we divide by for the percent error? Aha. So I like using the omega that we found using the period t. I think that's a more accurate value than the one using the fast Fourier transform. And Ben, where do we put the fast Fourier transform box again? You're welcome, Matthew. Ben, I'm not sure I understand about where you put the box. Let me see here. So I'm gonna pull up the Excel spreadsheet. Okay, so this column, and that's true for all the parts, that's where you have the period of oscillation, and that's the angular frequency you determine with that. And then here's the fast Fourier transform peak frequency, like I was at 1.367, and here's the angular frequency using that value. Oh, that box, you mean the gray area. Okay, got it. I wasn't thinking about box. I was thinking Excel boxes. Okay, so let me go to okay, so you're talking about this right here, the fast Fourier transform gray region. Is that right? Yes, okay. So with mine, my value doesn't change for that peak frequency. All the other ones are kind of moving around. Is yours changing here? I think maybe I should look at your software. Can you share that with me so I can see what's going on? Okay. It looks like you have two peaks. All right. So you kind of left click on the gray region just once, and then you can move it around. Just left click and don't drag. There we go. Yeah, I see that. Okay. Yours, for some reason, is having a terrible time trying to figure out if it's one frequency or the other frequency. That's amazing. All right. So I have a suggestion, because I was thinking about this yesterday. Since it's kind of competing between the two frequencies, and the two frequencies are really close to being the same number, put your cursor down on the FFT plot. And see, they're almost, that's 1.172. What about the other one, 1.367? I wonder if you just take the average of those two values, because they're so close in amplitude, they're trying to compete with each other. So my suggestion is take the average of those two numbers and use that. Sound good to you? Great. And then Brendan, which omega do we use for the graph at the end? Okay, so I haven't gotten there yet, but you can go ahead and start that. I use the omega for determined with the period, and they say that in the online manual too. So using the angular frequencies determined by the period t, use those in the table down below next to the graph area. So definitely not the ones with the FFT, because I don't think it's as accurate as the one we determined with the period t. Okay, you see, it's trying to, if you were noticing what Ben was showing, when we do the fast Fourier transform, it has these bins of different frequencies, and they're set values of frequencies. So when you move that area, that gray area over, it tries to see how many will fit into one bin and how many will fit in another bin. And so Ben was having a discrepancy between the two, or mostly you'll have very little discrepancy, and you'll definitely put a bunch of them into one bin of frequency. But definitely it's a value and not a shifting value to more easily or more accurately fit that value of frequency. But since we're choosing 4,096 bins, it makes that bin much narrower, so it's working as best it can. So yes, use the period t omegas in graphing. Okay, so I know Brendan is working on part 3. So your percent error at the end, you mean with the spring constant? Okay, Brandon's working on part 3, and Justin just finished. And Ben, what was the angular velocity formula for the FFT? Is 2 pi multiplied by f, Ben. 2 pi f. And then Brandon. So 10% is not too bad. And you're welcome, Ben. And Matthew, I'm working on part 3 also. Okay, go ahead and keep working, Matthew. So Brandon, let's see here. Yeah, 10% off. So what spring constant did you get from the graph? In other words, take the A value that you get from the graph and square it, and then tell me what value you get. See, Justin, sorry I may have missed it. Do we take the average of the 2 angular frequencies of each trial to use the... No. Use just the angular frequencies that you determine using the period t, not the ones using the fast Fourier transform. Okay, Justin? You're welcome. So from the graph, you're getting a spring constant of 14, or thereabouts, right? But the online manual says it should be closer to 11 and a half. Try this. Go back to your experiment 7 Excel worksheet and look for the spring constant you determined for the long spring for that experiment, and then write that one in the chat. I want to see if they're comparable to 14, if it's comparable to 14. Now, it's the long spring, not the short spring. Remember, the short spring has something close to 200, while the long spring has something closer to your 14, I think. So go back to experiment 7 and see what you got. You got 13.84. Hey, look how close that is to 14.04. Okay, now Justin, mass on the x-axis, right? Yes. In fact, I've got the table set up so the mass is on the left and the omega is on the right. So when you do a click and drag across the data set and you go to insert a graph, it'll put the mass in the x-axis for you automatically. You're welcome. So go back to Brendan. So what you can do in your write-up, let's see, with it being that close to the experiment 7, I may just run with this number for the report. Yeah, so go ahead and keep the 11.5 that the online manual says, and then of course the square root of 11.5. But let's say put it in the blank boxes to the right of each of those, put in your value of 13.84 and the square root of 13.84. And in your results section, you can write about both of them. So I'm thinking that even though, yeah, great. Even though the people who put this together and they gave us these long springs, and I think the majority of them are probably close to 11.5 the spring constant, but since they are like mass produced, some of them might have been like turned a little bit tighter than the rest of them and gotten a little higher spring constant, because it doesn't take much to change the spring constant. So I'm thinking that, just because they're all mass produced, they're going to have slightly different ones. They're kind of around the same number, but not exactly 11.5. And if anybody else is experiencing a number which is, more than 10% off, you might want to go back to experiment 7 and see what you got for your spring constant there, and use that number as a comparison too. Okay, so Brandon says percent error at the end is approximately 5.7. That's excellent. You don't have to worry about anything. Then Tyler is done with part 3, and Joseph is done with 3. Great. And I'm going to write the report. Thanks for your help. You're welcome, Brendan. Have a good day. And Kimberly's done with 3. Great. So we're getting some more people done with part 3. So I'm going to go on with my notes about graphing. and Justin says got a very high percent error. So we'll take a look at that, Justin. So in this last part, the analysis part, so here you graph the three mass values from parts 1, 2, and 3 with the corresponding angular frequency values, the ones determined using the periods measured, not the ones using the FFT. And this plot will have you fitting a power trend line, okay? Not a linear one, but a power one. And comparing the coefficient A with the square root of the stated spring constant in the online lab manual, which is supposed to be 11.5. And you take the square root of that in that next box down on the worksheet. As usual, the percent error value when determining comparison, the results portion of the report. Okay, so if I go back up to our equation, because this is the equation we're looking at, and we're looking at the power trend line fit, and we're going to get a y equals ax to the b, where a is supposed to represent the square root of the spring constant, and then that b should be really, really close to minus 0.5. Okay, so make sure that that's working out for you too. So I'm going to go to the Excel worksheet. I'm going to stop sharing this. I'm going to go to this worksheet. Okay, so you've got an angular frequency in part 1 using the period t. You've got an angular frequency using the period t for part 2. And again, you got an angular frequency in 3. You also got the three different masses from parts 1, 2, and 3. So down here, you're just going to copy and paste those three different masses from parts 1, 2, and 3, and those three different omegas that you got from parts 1, 2, 3 when you were determining with the oscillation, the period t. That's what goes there. And then you just go ahead and click and drag across that data set and insert a graph over here. And you're going to get, it's only 3 data points, but when you do the add trend line, because you want to go there and add trend line, make sure you go to more options and you want to choose the power fit, not the linear fit. This is definitely a power fit. And you should see, like you'll get a data point here, a data point here, and a data point here. So it's going to have a swooping arc of this kind of shape. And then you put the equation up there, and you should get your A value. And the A value should be, ideally, close to, not 11.5, but the square root of 11.5. So just go down here and then type in equals square root of 11.5. And you get that number, 3.39. So around 3.4. And that should be your A value. But then it could be off a little bit, because when you do the percent error, if it's more than 10%, have a look back at your experiment number 7 and see what spring constant you got from there. If it's kind of far off from 11.5, go ahead and type in here what value you got, and then type in, and then go ahead and take the square root of that value here, and then do another comparison for percent error and see there. And if it's a smaller percent error, or closer, then do both, or write about both in the results section of your lab report. Okay. Whoops. See, Justin, the experiment said I got 13.99. Okay, so if you take the square root of 13.99, Justin, is that closer to the A value in today's experiment? My percent error went down to 9.2 using the 13.99. Okay, so So using the A value from your graph, square that number and tell me what that number is in the chat. So square your A value and tell me what it is in the chat. 16.7. Wow, that's huge. So to me, that might be something wrong with the data a little bit. Because it's so large. But we'll just have to see what's going on. So let's see. I wonder, can you go ahead and share, Justin, can you share your Excel spreadsheet? I'm sure what kind of data you have. Okay. Wow. Okay, Matthew. I forget. What did you get for experiment 7's spring constant? Okay, so we got Justin, and you got 4.807. You got 12.5. So that's quite a discrepancy, Matthew, between the two. So even though you got 12.5 instead of 11.5. But I'm gonna get back to Matthew, and I'm gonna work with Justin right now. So you got that, and you got that, and you found a percent error down below, or like 9%, you said? Yeah. So I would change that. Don't use that box for the comparison with your other K value. Make that comparison to the 11.5. Yeah. And then use that one. Yeah, do that one for you got it. Very good. Okay. I'm still wondering why you're getting such a high number. Can we go up to your part 1, part 2, and part 3 values? So for part 1, I want to see your mass. You got 0.1994. Okay, that's really good. Then you added mass to it and got 0.28. Then you added more mass and got, what's that, 1.37. Okay. And it's showing proper change in angular frequency. And you got 8.3, 7.07, and 6.33. And then go ahead and drop down to the table for the graph. All right, so you've got that. Okay, just go with it. This is it looks like you're doing well enough because your percent errors and your megas are pretty small, right? And Tyler, you don't have any questions? Oh, Justin, I just want to make sure that your megas are pretty close together, weren't they? They had small errors for each of your megas for part 1, part 2, part 3, comparing the two omegas. Okay, Tyler, have a good week. So I'm good with that too. It just might be that the number that you got from experiment 7 might be off a little bit also because it isn't, you got it from data. So it might have actually been smaller than what you actually found from before. But at least you know it's not 11.5 and it should be a little bit larger. Does this sound good, Justin? Great. Every time we do an experiment, we have, we think we have a value, but that value could be off a little bit from the true value. We just never know what the true value is. We just have to have uncertainty analysis to help us, get close enough to it. Or get better experiments, which will narrow the uncertainty down so we know we're getting better values. You're welcome, Connor, and you're gone. Okay. So is anyone else getting good values, bad values for the spring constant after we finish the graph? Or is anyone still working on part 3? Matthew got bad? Bad. Okay. And Nathan's on part 3 still. Okay. So keep working on part 3. And then I'm going to get back to Matthew in a second. And then Joseph says, my A value for my graph is vastly off. Would you care to take a look? Yes, let's have a look, Joseph, and then I'll get back to Matthew. And Tara's still on part 3. Okay, keep working on part 3, Tara. This is Joseph. See Ben on part 3. Nothing has worked the first time, so I'm a little behind. That's okay, Ben. Just keep working. All right, so let's see here. You got your mass. Okay, yeah, 0.2 and then 0.23 and then almost 0.26. Okay, that's not a bad. Okay, that's not too bad. And then can you go to your the graph? Go ahead and click on the graph and get those. Yeah, go to the plus sign for the off the right, and go down to the trend line, and go to more options, and something should show up. Okay, so there's the power. All right, so you got the power on there. And for some reason, even if you look at the equation, even your exponent on the x is not anywhere close to negative 0.5, which it should be. So there's something really going on here. But you have the data, and you have 7.9, 7.5, and 7.22. All right, so, and you're choosing power. You've got that. So it must be the data. So let's go back up to part 1. And you have an angular frequency of almost 8 and an 8.5. Okay, and you have 1.367. Time between. Okay, if you can click on the period of oscillation t, where it says 0.791. Okay, so you took that and divided by 5. All right. And you had 3.955 for that time. And then go ahead and click on that one. Go ahead. And you had 2 times pi divided by that, and that's that. Okay, let's go ahead and if you click on that one also, and then down below the 7.5, and that's, yep, same equation. Then you're getting closer to the FFT value, only almost 3%. And then down there is like 2% error. So I'm wondering if it's your mass, which is off. So try this. Go back to the items you had for part 2 and have those attached to your iLab and go through the process again of determining the mass. But before you do so, calibrate again. I mean, it can happen. Calibrate again the force probe and the accelerometer, and then go through the whole process of determining the mass. You might want to do it for all parts, part 1, part 2, and part 3. So do that again and see if anything changes. All right. Now, Matthew. Where'd Matthew go? So Matthew, you said bad. Let's go back to bad. Okay, hi Matthew. So what's going on with your data that you're saying bad? So race 7 A value is much better than the A value for my graph. Okay. So what value did you get for what's the square of your A graph? The A from your graph. If you took the A value from your graph and squared it, what number do you get? Down there. Okay. So that A is the square root of your number, right? So 3.5. Yes, okay. I'm going to get my calculator up here. So 3.56. It's around 12.5. Okay. Yeah, because my spring, I usually get a spring constant around 12. and they say 11.5. So in your case, I would do the same thing as one of the other students, is to report on both values. Report on the 11.5 that the people who wrote the lab manual stated as, and saying you're getting like almost a 21% error. And then using the spring constant you found from experiment 7, show that you're getting a percent error, which is far less, less than 5%, and then just write up your results section that way, reporting on both. Does that sound good? It looks like your data's fine.